All right, folks, here we are, section 3.3 on Bayesian linear regression. Okay, so this is going to be talking about how to do linear regression in a Bayesian way, in contrast to kind of what we just saw, where we're doing things in a frequentist way, kind of reporting a single number, for example, for the maximum likelihood estimate of the mean, and then we saw how we can use things like the Bayes variance decomposition to get a handle on how good that estimate is. Well, the Bayesian approach tries to do things it does things differently by essentially just using all of the probability information that we have and bringing it along, as far as we can. So rather than, reporting single point estimates, why not just report a distribution on the parameters, and that essentially then encapsulates all of the data. So you're not just limiting yourself to a single pair of numbers, but you're saying here's my entire uncertainty over these parameters given my model and the data that I've observed. So we'll see how that works. In this video, we're just going to cover this first section on the parameter distribution, and it comes with this really great example, which we're going to go through. And I've got, at the end, I've got some code to reproduce this, so you can try it at home and see how it all works. But you don't have to do that. The main idea is just is already captured in this video. So the code is just for fun for you to play around with if you want. Okay, and we'll talk about that at the end. All right, so let's get going. Okay, so he says, and you guys can all see. Okay, great. So in our discussion of maximum likelihood for setting the parameters of a linear regression model, we have seen the effective model complexity governed by the number of basis functions needs to be controlled according to the size of the data set. So we added this kind of regularization term. The log likelihood means the effective model complexity can then be controlled by the value of the regularization coefficient, although the choice of the number and form of the basis function is of course still important in determining the overall behavior of the model, right? So remember, the geometric intuition for that was each one of those basis functions is going to kind of give you a direction in data space. Remember that vector of data that we would have, and that t vector that would have our data points for, from time, our first to our nth data point, and then our feature vectors evaluated on our inputs gave us gave us vectors in that data space. And the more of them we had, the closer that the span of those vectors could get to our data, but then we ran the risk of overfitting. And so that's where we brought in the regularization to try to help with that. But the question is, how do you pick the regularization term, etc. Okay, so he says this leaves the issue of deciding the appropriate model complexity for the particular problem, which cannot be decided simply by maximizing likelihood function, because this always leads to excessively complex models, right? Because you don't know what's signal and what's noise, right? So if you have like 10 basis functions, you'll use them all to fit your data, but little do you know that actually, most of that variability you're trying to explain, maybe it's coming, or at least some of it is coming from noise. How do you know? It's just, it's just a data point. Right, so yeah, so there will always excessive complex models overfitting. Independent holdout data can be used to determine model complexity, so kind of doing cross-validation, things like that, but this can be both computationally expensive and wasteful of valuable data. So now we're going to turn to a Bayesian treatment of linear regression, which is going to avoid the overfitting problem, and which will also lead to automatic methods of determining model complexity using training data alone. Now, as we'll see at the very end, he will, not of this section, I think it's like a couple of sections from now, he will say that in the end, it probably is still worthwhile to keep some data on the side to do the cross-validation, but at least you'll see how to do it in principle, how you don't have to actually split your data sets, reduce your statistical power, whatever it is, by limiting, your estimation to 90% of your data, and then so that you can evaluate on the other 10%. There is a principled way of just using your entire data set, which we're going to see. Now, whether that's practical in most cases, or in some cases, sometimes it is, sometimes it's not. So it's good to know both. But at least in theory, there is a way that you can use all of your data. Okay, but so in this particular section, we're just going to look at how how in the Bayesian setting the parameters get updated. It's kind of what we keep around, and that's going to be the whole uncertainty on our distribution, on our on our parameters, given within the bounds of our model. Okay, again, for simplicity, we will focus on the case of a single target variable. Okay, so it's just going to have a single channel. We don't have this going to be a multi-channel situation. Extensions to multiple target variables is straightforward and involves the discussion that we already chatted about. Okay, so this is what we're going to talk about, the parameter distribution. W, what's going to be the probability on W given the data. So we begin our discussion of the Bayesian treatment of linear regression by introducing a prior probability distribution over the model parameters. So again, it's in the Bayesian setting, you always need a prior on the parameters. And that's going to be, people are going to discuss, argue about that, but the cool thing about it is you have to be explicit about it, so at least people will have something concrete to argue about. If they don't like your prior, they can suggest a better one. So it gives you kind of something to do rather than just complaining. Okay, for the moment we shall treat the noise precision parameter beta as a known constant. You'll see where it comes in. Now first note the likelihood function. So this is P of t given W, given by 3.10. I won't scroll up. I think this is, well, let me just grab it from the book and I'll write it in here so we don't have to scroll so much. Okay, 3.32. Yeah, right. Okay, so here it is. This is what he's talking about. I will just write it in for you. So this is the one that just says, the probability of this big data vector given, your inputs, W, beta. This is just saying this is going to equal to the probability of the individual data points, because we're assuming that things are independent. So this is the thing we care about. And then we've got phi of x of n, and then we've got 1 over beta. So that's our position. Okay, so that's what that is. Okay, we shall treat the noise precision. Okay, first note the likelihood function is the exponential of a quadratic. So this is because this was going to be then, remember this was going to be ti given wt. And did I write, sorry, yeah, exactly, it's already actually in there. This should actually be, I wrote this as a p, but it should actually just be a normal distribution already. So that was not very helpful. There's a normal distribution. Okay, so this is going to be the exponential of a quadratic function of w. That's coming from the normal distribution. And the corresponding conjugate prior, remember we talked about these? And the point of the conjugate priors was so that the posterior would be in the same family as the prior. And we know that the conjugate prior, when your likelihood looks like this, is also given by a Gaussian distribution. So here we go. So the prior on, so this kind of, again, we're doing this, notice that we're doing this for mathematical convenience, right? So there's no, in real life, there's no reason that your prior on your W should have this form or any other form, like that's sometimes something you have to just get from the data, your prior knowledge, etc. But here we're going to do this to make our life mathematically simpler, because we just kind of want to see, like, in the ideal setting or in an easy to analyze setting, what do things look like? In a real setting, the qualitative picture will be the same, but it will be harder to figure out what's actually going on. So we use these simple examples where we can work out everything mathematically to give us an intuition for what's really happening, but it's less accessible in more realistic settings. Okay. So here's the conjugate prior. So we've got m naught, so that's like your prior mean, and some prior covariance on your weights. Okay. And next we compute the posterior distribution, which is proportional to the product of the likelihood and the prior. This is Bayes' rule. Now due to the choice of conjugate Gaussian prior distribution, the posterior will also be Gaussian. That was the whole point of picking the prior the way we did. We can evaluate this distribution by the usual procedure of completing the square. So I think that's actually good practice to do, to go and make sure you get these results, but we've already done it before, so you can just save yourself the trouble and just look up the answers. And then finding the normalization coefficient using standard result for normalized Gaussian. However, we've already done the necessary work, so the answer is here, which allows us to write the posterior distribution directly in the form of, so this is now the posterior on W given the data. And now you've got your normal distribution again, obviously it's going to be on W. But now we have this kind of mean that's being computed after n data points and the covariance. And actually, like for this, in this particular setting, they're kind of actually easy to remember, more or less. So maybe the easiest one to remember is you're going to have the precision. So this is Sn minus 1 is the precision. Is the prior precision plus the precision from the data. So it's kind of additive. And if you do kind of one data point at a time, you'll see that you just get precision from each data point contributes kind of one of these precision terms. And the mean it's a precision weighted combination of the prior mean and something that has kind of to do to the data. Now, it doesn't quite look that way here, but let me just put it for you. So suppose, remember that, t, we can write t as actually being, or I'm going to say approximately equal, because it might not be possible to exactly get t into the span of w. So maybe it's like this is t and this is phi w. So this is kind of the closest you can get. So this is phi w, which is the closest you can get to t. So if we now write this expression and replace t with this kind of vector t with phi of w, so what we'll get is, this is s of n, so minus 1. Notice that so minus 1, this is a precision. So we're weighting the prior mean by precision, plus beta times phi transpose phi of w. And let's call this, I don't know, w hat or whatever it is, w from the data. And now look at what we have. So the next thing is just to write this Sn as Sn minus 1 to the minus 1. And what I'm trying to kind of make you recall is that we had a similar situation in the one-dimensional setting, where instead of Sn we had, there was a precision, right? So we had, there was a scalar precision. So there was like a, there was a lambda after n steps, minus 1 times, there was like a lambda of the data plus lambda of, what are we going to call it? I don't know, lambda hat. Let's just call lambda hat of some new value that you were getting from the data. So you can just write this as, and remember, lambda n was just equal to lambda, the precision from the prior, plus the precision contribution from the data. So in the end, you got that your estimate after n steps was a weighted combination of the input from the prior and the input from the data. So this is exactly the same thing here. So if you just remember that, you will just remember this formula. You don't have to memorize it. You don't have to memorize these things anyway. You can look them up. For the Gaussian case, I think it's actually kind of useful. It'll come up quite a bit. And it's cool to kind of just see how it works. Okay, so let me just erase all this stuff. Yeah, there we go. Okay, so this is what happens if we, and remember, what's t here? So t is our, t is our data points all the way to Tn. So this is a vector of all of our data. So essentially what we're doing is we have a prior, which we had, with S naught and M naught, which is over here. And we've observed n data points, and now we update our mean and our precision with that data. Okay, and so notice that we're just reporting, so we're not reporting a single value, we actually have this whole distribution. In this particular case, it's actually easy to work out what the parameters of that distribution are. Note that because the posterior distribution is Gaussian, its mode coincides with its mean, right? So the highest value, the most likely value, is also the mean value. So the maximum posterior weight vector is simply given by W map. So if we wanted to do a map estimate, so we don't want to give any uncertainty information, we would just report the mean. If we consider an infinitely broad prior without, alpha precision, or this is our precision and it's going to 0, which means the variance is becoming very, very high, going to infinite, the mean M of n of the posterior reduces to the maximum likelihood value WML given by 3.15. So the point, all that is saying is that if the prior isn't giving you any information, all the information is going to come from the likelihood. So, the thing if you want to report a single value, this mean value, it's going to be the maximum likelihood estimate because there is no prior information. Similarly, if n is equal to 0, then the posterior distribution reverts to the prior. So again, natural, but the other way. Furthermore, if data points arrive sequentially, then the posterior distribution at any stage acts as a prior distribution for a subsequent data point. And that's kind of what we're going to be using in the example and in the code. Okay, so for the remainder of this chapter, we shall consider a particular form of the Gaussian prior in order to simplify the treatment. Again, just want to see how things work in a simple case. We'll consider a zero mean isotropic Gaussian. So isotropic means it just has the same variance in all directions. So this is just, so your variance is going to be alpha 1 over alpha times I, the same in all directions. Governed by single precision parameters, so that so we got this kind of prior on the weights. The mean is 0 and the variance is 1 over alpha times I. And the corresponding posterior distribution over W is then given by 3.49. So we just plug in, these values. So notice that, so this mean contribution disappears, the prior mean, because it's 0. So all you get is just the contribution from the data. And then your variance, well, instead of S0, you just get alpha. So it's quite a bit simpler. The log of the posterior distribution is given by the sum of the log likelihood and the log of the prior, and as a function takes the form so and so. Okay, so look at this. Look at what we've got. We've got the prior coming in, and we've got the likelihood terms. Maximization of this posterior with respect to W is therefore equivalent to the minimization of the sum of squares error function with the addition of a quadratic regularization term corresponding to this with alpha equals 1. Okay, so this is probably quite clear to you. It's, it's an important point, but it's one that we've actually encountered a few times. That actually, when we're doing, when we're maximizing, when we're maximizing kind of these energy terms and regularizing, well, it actually has a probabilistic meaning. And that's one of the really cool things about it. We've discussed this a few times, but it's good to see it again. So essentially all he's saying is, well, if you just divide everything by beta, so if you maximize ln, the log posterior divided by beta, you would still get the same point of the solution, and now you would get 1 over 2 alpha over beta. So this would be your, your penalty, your regularization penalty that we had before, and this is just your ordinary error, this error function that we've been minimizing. So I think it's, again, bears repeating. Minimization, this link between these error functions that we maybe heuristically come up with, and then their probabilistic interpretations. Okay, so now let's go and work on the example. So we can illustrate Bayesian learning in a linear basis function model, as well as a sequential update of a posterior distribution using a simple example involving straight line fitting. So this is going to be a really cool example. Okay, so we have single input variable, so one-dimensional, a single target variable, and the linear model of the form y of x is equal to w0 plus w1x. Okay, so as we will see, our data kind of look like this. Because this has just two adaptive parameters, we can plot the prior and posterior distributions directly in parameter space. Okay, so we generate synthetic data from the function we've got these true values. We're going to generate some data from it by first choosing values of x of n from the uniform distribution from -1 to 1, and then evaluating f of xn according to this, and finally adding Gaussian noise with standard deviation of 0.2 to obtain the target values tn. Okay, so all he's saying is, we're going to generate these data, but we have some true line that's kind of going this way. We pick a point at random on the interval. We pick a point on the line, add some noise to it. So that's how we get the data. Our goal is to recover the values, so let's just highlight this. And we'll explore the dependence on the size of the data set. Okay, so I think for this section, we'll go through the figures again when we get there, but it'll be useful for you to be looking at these figures at the same time, because I can't really I can't read this page and also show you the figure. So we assume here that the noise variance is known, and hence we set the precision parameter to its true value. So somehow we know what the variance of the noise is. And I think in real life, it's not too unrealistic to assume that you would know the variance of the noise. So for example, we have, when my colleagues do kind of recordings of neural activity, well, there'll be periods where we know, okay, there isn't much activity, like maybe the stimulus hasn't been presented, etc. And so you can often use that period to kind of get some kind of estimate for the noise. So it's not necessarily such a bad assumption that we know what the noise variance is. Sometimes you can estimate it using these kind of signal quiet periods in your data. Similarly, we fixed the parameter alpha to 2. So this is, again, so now this is kind of a little bit harder to choose. You might have some prior information on kind of what the prior on your weights should be. So yeah, that's just something you're going to have to kind of provide or have a good guess at. We shall shortly discuss strategies for determining alpha and beta from training data. And now this figure that we're going to talk about shows the results of Bayesian learning in this model as the size of the data set is increased and demonstrates the sequential nature of Bayesian learning, in which the current posterior distribution forms the prior when a new data point is observed. So again, the point here is, and we've discussed this before in the sequential estimation section of the previous chapter, and the idea is that, well, you know, you can just always, this is your posterior. Well, what if you get more data points? Well, you can just use that posterior now as your prior, and it incorporates your actual prior, but then also incorporates all the previous data points. And so you can do things sequentially. You don't have to do them like one data point at a time. You could do them, you know, whatever is convenient, however the data arrives. But the point is that you know, the posterior then becomes the prior for the next. And this is just really another beautiful aspect of the Bayesian approach. Like, you know, this sequential estimation it's just kind of a natural. It just emerges naturally from it. So yeah. Okay, it's worth taking time to study this figure in detail as it illustrates several important aspects of Bayesian inference. Indeed, and so we are going to study it in detail, and there's going to be code that you can play with, so you can see how it's all done. But again, it's just, the code is simple. It's just essentially just running these formulas basically. Actually, yeah. Okay. So the first row of this figure corresponds to the situation before any data points are observed and shows a plot of the prior distribution with 6 samples of the function in which the values are drawn from the prior. So that's before, we'll look at it in a sec, but that's kind of before we have any information. Our prior on the parameter says, well, they could be anything, so that means the line could be anything. In the second row, we see the situation after observing a single data point, and we show where the data point comes. In the left-hand column is a plot of the likelihood function for this data point, and note that the likelihood function provides a soft constraint that the line must pass close to the data point, where close is determined by noise precision. So this is like a really cool, just a really great way of kind of getting intuition for how these functions work, right? And you'll just see it in a sec. For comparison, the true parameter values used to generate the data are shown by white cross. When we multiply this likelihood by the prior from the top row and normalize, we obtain the posterior distribution shown in the middle. So let's just highlight that as well. Again, just showing us how to do this kind of updating the posterior. Now, samples of the regression function obtained by drawing samples from this posterior distribution are shown in the right-hand plot. So basically, now that we just do the same thing we did before, but before our prior was isotropic, so you know, the weights could be anything, so then the lines could be anything. Now we have a single data point, which is going to constrain our weights, and then that'll show up as the lines being constrained. Note that these sample lines all pass close to the data point. Like, amazing, right? It's kind of a beautiful thing to see it happen, honestly. Like, it's just heartwarming to see it happen. The third row of this figure shows the effect of observing a second data point, again shown by a blue circle. The corresponding likelihood function for the second data point alone is shown, obviously. When we multiply, note that we obtain the posterior exactly the same as before. An important thing he points out is that note that this is exactly the same posterior distribution as would be obtained by combining the original prior with the likelihood function. So essentially what we're doing here is we're going one data point at a time, but what he's saying is you will get exactly the same answer if you just take those first 2 data points, you know, and so your n would be 2 in this case, and you just combine it with the prior. So you can do things sequentially, like in maybe in online applications, it makes sense to do things sequentially. You can also do it in batch. They'll give you the exact same answer. So let's, you know, this is an important point. And it will also be useful for you to go and show it to yourself. Like, try computing it 2 ways with the 2 data points analytically. Just show yourself, convince yourself that it actually gives you the same answer. Okay. Oops, and I meant to actually highlight this thing. Okay. This posterior has now been influenced by 2 data points, and because 2 points are sufficient to define a line, this already gives a relatively compact posterior distribution. And samples from this posterior distribution give rise to functions shown in red as before. And the fourth row shows the effect of observing a total of 20 data points. And you can see the likelihood just for the 20th data points. The likelihoods are always going to look about the same thickness because it's doing it 1 point at a time. The middle plot shows the resulting posterior distribution that has now absorbed information from all 20 observations. So, the precision is kind of always increasing. And so the covariance, the variance is shrinking with every single data point, which is kind of an interesting property of this model, that no matter what the data points are, at every iteration, your precision is going to increase. So your variance is always shrinking. Yeah. Note how the posterior is much sharper than in the third row. In the limit of an infinite number of data points, the posterior distribution would become a delta function centered on the true parameter values shown by the white cross. Okay, so let's go look at this figure ourselves again in some detail. Yeah, you guys can see everything. So again, this is the likelihood. This is before we observe anything. Here is our prior. It's just a prior at that, and we've just sampled some lines. So you pick a W from here and you draw the line basically, and you see we're getting all sorts of lines. Now we get a single data point, so now we have this likelihood, right? It says that, this is our data point, and it says that, and I think this is a true value, I believe. Yeah, I think that's a true value. So we've got this data point, and now it says, and this is kind of the likelihood of the data for that point. So these are kind of the sets of weights that would result, just if you forgot about the prior, that would that are consistent with this data point right here. And so we now look at the posterior distribution, and now it has an interesting shape. It's gotten shaped. And you can kind of look at it, and it's got kind of, first of all, you can notice that it's obviously this times that, right? So everything in this, where the likelihood is low, the prior will be low as well. So, and the peak is going to be where both the posterior and the prior, have some mass. So we get this kind of, this ellipse showing up. And notice kind of what it tells you, right? So it says, well, essentially we can kind of get, it's telling you either the weight, the offset, which is W naught, either it's very negative and the weight is positive. So that's on that line. So either we're kind of like looking here, that's one corner of the data. Or the other extreme where we've got the weight being large and we've got negative slopes. So either it's positive offsets and negative slopes, so that's kind of these kinds of lines, or it's negative offsets and positive slopes, that's those kinds of lines. So it's kind of telling you that's where the data lives. I mean, the most likely value here is actually, if you look at it, we don't see much here, but it says, well, actually, these kinds of lines are the most likely, but we're sampling right now, so we're not picking the most likely value, we're just sampling from this distribution, and so we're going to get points from this extreme, which is going to be, I guess, point lines like that. We're going to get points, over here, which is going to be lines like that. And if we sampled some more, and you can do that in the code, you should get lots of lines that are essentially from here, like that. But they all are going to want to go through, at least go close to this observed data point. And now we get, okay, 2 lines. So now, okay, already with 2 data points, it becomes clear that, okay, we're definitely not flat. We're certainly not this type. So it's going to be like this. So we're going to have a negative offset and a positive slope, and that's essentially where the data is focusing. And as we collect more and more data, well, then we just get closer and closer to the true value. Notice the likelihoods again are always of they look the same thickness, and that's because we're just doing the likelihood for one data point. They're all independent. But each time what happens is you take the prior, you multiply by the likelihood, renormalize, and you get a distribution. And by the time you've got 20 data points, it's pretty clear. There's still some variability, but it's pretty clear what it is. And notice now you've kept this whole distribution. You can choose to report the maximum value if you want, but you can also just report why not report the whole distribution? Or if you don't want to do that, maybe report the maximum value and some measure of the uncertainty. And you can kind of choose what you want to do. It doesn't have to be so ad hoc. And if you have to make an approximation, you can kind of do it in a meaningful way, rather than just kind of crossing your fingers and hoping for the best. So that's kind of what that's about. I think it's a really cool figure, and and the code that I provided will kind of allow you to create that yourself. So maybe actually now is a good time to switch over just to show you what we have there. So there we go. Let me increase the size a little bit. So I'm going to put a link to this repository so you guys can see. Obviously, yeah, so you can see what we're doing, how it all works. It's all pretty straightforward. Yeah, so loading all the Python stuff. Here, look, we're generating the data. This function generates the data. You give it a true, with true values of A, I think, and you know the precision and the number of data points you want. So it picks points at random, uniformly at random from -1 to 1, and just generates data. So it generates the data in one step. It just generates the Y value and then adds noise to that. There we go. So that gives you X and Y. Here, this is a function just to draw the lines, right? So it'll draw a line from -1 to 1 of given whatever A. So that's going to be useful for producing those plots on the right where you see what a given parameter, the line that it corresponds to. This is kind of a function that will plot the contour plots, right? So you give it a function, and now it will then just create a grid over -1 to 1, and then it will evaluate that function, the function you've given it, at each one of those data points. And then it'll just, so that's Z, and then it'll just plot a contour plot of that function. So that's going to be used in plotting the posteriors and the likelihoods. And these are kind of the functions we're going to use. So the likelihood function, where you give it X and Y. So the likelihood for a data point X and Y with this with the precision beta. So it's going to return a function where you, again, remember the functions we're going to be plotting are going to be posteriors over the parameters and likelihoods of the parameters. So they're going to take A, which is going to be the two different weights, and then plot, compute, for example, the likelihood or the posterior. For the posterior, you need the mean and the precision. So given that, then for any parameter, pair A naught and A1, it'll give you the. And here I haven't normalized it because for the plots it doesn't matter. All that matters is kind of the relative values. Well, and so these are the values you would get. Okay, and then finally, we're going to sample, get some data points, 100 data points. These are the values that we've used in the book. Here is our precision, a random seed that produces data that kind of looks like what's in at least the first couple of data points are similar to what's in the book. Generate the data, and now we're actually going to do the actual estimation. So this is our prior parameter alpha. This is just the identity matrix, and now we're going to keep a history of our means and our precision as we're updating them. And notice that, so we're doing things one at a time. So our phi vector just becomes, there's one value. Our very first feature, just like before, is just the ones feature to allow for offsets. And our second feature is just the data. So it's kind of these are linear features. And we compute this kind of transpose matrix that we need, update the precision, update the mean. So this might look a little bit mysterious, but this expression is just equivalent to taking the inverse of the precision and multiplying it by this term, which is what we're doing in the book. So instead of having to invert, you could just invert prec underscore n and multiply. This is, especially, I think it just has a kind of better performance, better behaviors, but you can do it whatever way you want. Keep track of that, and then in the final section of the code, we actually just plot the results for the data iteration that we care about. So this is kind of the first data point, the second data point, and then we've got 20 data points. You can see kind of how the plotting works. And at the end, we get, a curve like, plots like this, which just show you just like, we have in the book. You start with the prior and the posterior, and then you progress, keep getting the likelihoods, combining them with the priors from the previous step, or i.e. the posteriors from the last step, and until you eventually have, until you eventually get 20 data points, and it's quite clear what the function is. Okay, so I'm going to put a link to that so you can play with it if you like. Let's now just go back and finish off with just one tiny little section in the book that we need to, one tiny paragraph. So let's go and do that now. So I'm going to turn this on, turn that off. Great. Okay, so all he's saying at the very end here is other forms of prior over the parameters can be considered. For instance, we can generalize the Gaussian prior to give this exponential. Now notice that is a sum of the absolute values of q's instead of 2. So in which q corresponds to the Gaussian distribution, and only in this case is the prior conjugate selected. So if we use a different Q, well, you can still do inference, but the math isn't going to be so nice. So you might have to use numerical methods, etc., to do it. But sometimes you want to do this. So for example, if you want, sometimes you want kind of sparse weights, then you want some of them to be identically 0. We kind of talked about this. Q is going to equal to 1, and that will have nice properties in terms of its output, but now it'll be harder to analyze, it'll be harder to see what's going on. So that's why it's useful to actually look at these simpler cases where Q is equal to 2, where we can analyze everything to really understand, get an intuition of what's going on before we try more complicated but maybe more relevant situations for us. Finding the maximum of the posterior distribution over W corresponds to minimizing of the regularized error functions. This was the one where just W, instead of having the norm of W squared, it was the norm of W to the qth power. In the case of the Gaussian prior, the mode of the posterior distribution was equal to the mean, although this will no longer hold if Q isn't equal to 2. So he's saying that in general, when this changes, you're not, if you want to do the map estimate, well, that's no longer going to be the mean anymore. It might be something else. You might have to figure out what that actually is. It might not be necessarily where the functions peak. So just watch out for that. Okay, so I think that's all I wanted to talk about. I think it was a nice little section, and I think this figure I think is a terrific figure. I think definitely worth really understanding what's going on. Really gives you a lot of insight into the sequential estimation and the Bayesian approach. So next time we will talk about the predictive distribution, where we're going to be integrating, predicting the target values by integrating over our uncertainty. So really fun, really important section, and I hope you'll join me then. Talk to you soon.